Okay, let's talk about periodic trends when it comes to electron configurations and how those elements are placed on the periodic table. The fact is it's very relevant to how those elements behave. And we've already talked about the fact that your periodic table is arranged, and I showed you my wonderful drawing of you have this basically staircase. I'm not going to draw the whole thing today, but here you have your metals. Over here on this side, here you have your non-metals, and then along the staircase I drew for you, you have your metalloids. Now, let's think about metallic character. Here you see on this slide that, and this is in your text in the chapter, that metals do tend to be shiny. They're lustrous, which means they glow. They're malleable. Malleable means that you can hammer them into sheets or shapes, make shapes out of them, like bowls or tin roof, tin foil. They do tend to be good conductors of both heat and electricity. We already talked yesterday also about them having low ionization energy, which means they want to lose their electrons so that they can become like noble gases. They have too many in that outermost energy level, especially the group 1 and 2As. All those group 1As, they only have one one electron stuck out there in its outside energy level. They have one valence electron. If they could just lose that electron, they could become like a noble gas. And so how easy is it going to be to lose that electron, and how little energy would you have to give that element to have to give that electron up? So they have very low ionization energy, and that means they're going to become cations, positively charged ions. So they do tend to form metal chlorides like sodium chloride, magnesium chloride, strontium chloride. We've named several of these. And they also tend to form what are called metal oxides. And these are quite important in industry. You're going to have some questions on that on your homework quiz. Then you have nonmetals. Remember, your nonmetals are to the right on the periodic table, on the right side of your metalloid zigzag, and they usually are very dull. They're usually very brittle. So if you tried to hammer them and make a sheet of foil out of them, they're just going to break or crumble. Think of charcoal, like you make charcoal briquettes, like for your grill. You try to hammer that, it's not going to hammer into a nice sheet for you. It's going to crumble. That's a nonmetal. That's made out of coal or carbon. They're going to be very poor conductors of both heat and electricity, and they're going to form acid molecules, acid compounds with oxygen, like carbonic acid, like things like that. Hydrogen carbonate, those types of things, they're going to also want to gain electrons. So they're going to have very high electron affinities. They're really going to want to hold on to those electrons. And so they're going to hold them tightly. So that means they have a very high electron affinity and a very high ionization energy as well. Let's talk about the metallic character of things. Think about this for a minute and why it would be. Metallic character increases. It increases as you go down a group. Now, metallic character, metals tend to want to lose their electrons. Who's going to be hanging on to their electrons the least? The larger it is, the farther those electrons are away from the protons, and it's the protons that are pulling them. So the farther those electrons are away, the less pull. So the farther you go down a family or a group, the more loosely those electrons, those valence electrons are held, and the less ionization energy they would even have. So the more like a metal they're going to act. So they're going to increase their metallic character going down a group, and it's going to decrease going across, because you understand they turn into nonmetals going across this way. So more metallic going down, less metallic going across. That makes sense, yeah? And then metalloids, remember, they have properties of both, somewhere in between metals and nonmetals. And we've talked about these two. These are your D block elements, the ones that are in the middle. Okay. Keep in mind, we've been talking about the representative metals, those that elements, those that have the S2 and the P's, the ones that have the S's and the P's. But what about the D's? We've also talked about what does it mean to be isoelectronic. I talked to you about that in both of your other videos. Isoelectronic means they have the same electron configuration. And remember, everybody wants that electron configuration that the noble gases have. They want an S2P6. They want an S2P6 if they can get it, or if they're closer to hydrogen, like beryllium and lithium, boron, then they'll settle for an S2. Okay, if it's a 1s2, they'll settle for that. But they want an S2P6 as the octet rule. All right, it's called isoelectronic. And we've talked about that when they gain or lose. So here's your electron configuration for sodium metal. And when it loses its electron, now this is its electron configuration. So here's, right here, we've learned how to do this last chapter. Here's your electron configuration for the sodium metal, the atom. Now when it loses its electron, which one does it lose? The outermost. So this one is gone now. So now this is the, and you'll notice that this is the exact same identical electron configuration as neon. If you add these up, 2 plus 6 is 8, plus 2 is 10, has 10. So this is the exact same electron configuration as neon, and we did discuss that last chapter as well. So this ion, it's like it can't even tell the difference between it and neon, except that it has this charge. So it is not an atom, it is an ion because it carries that charge. But it will take it because it has that exact same electron configuration as the noble gas neon. So it's happy. Chlorine, same way. It doesn't need to lose. It would either have to lose these 7 and be like neon, or it could gain one more and have the S2P6 and be like argon. But now you see it has a charge of +1, and they're called isoelectronic, which we talked about. Okay. All right. And again, you could write these. You could write for the element itself, nitrogen, and then once it gains 3. For barium, the element, and then once it loses 2. All right. But what about the D block? What about the D block? Here's the D block elements. And what it says here, this is section 7.5 in your text. Where do they lose their electrons, their outermost electrons from? It turns out they don't lose them from the D's. They lose them from those 4 S's. Instead, look at irons. Electron configuration, here it is. It's argon, 4s2, 3d6. But when it becomes an ion, F2, it doesn't lose them from the D block. It loses them the 4s2s, not the 3d6s. It loses them from that outside shell. It keeps the D's. So when you're writing your electron configuration, be careful about that. We won't do as many of those as we will the others, like the S's and the P's. Because bless its heart, iron does not have a hope to get to be like a noble gas. Okay. And then we talked about these. Atomic radius. I challenged you at the end of the last video to decide what's going to happen to the ionic radius. What happens to, let's go back here. Let's talk about these two. Let's talk about these two. Here is the atom sodium. Here's the atom sodium. It has equal numbers of protons and electrons, so it is even. It does not contain a charge. And we know what its relative size is. You know, here it is in its little row on its little column on the periodic table. It's number 11, so there it is in its little group 1A family. Okay? But what happens when it loses that one electron? What happens when it loses this electron and it's no longer there? Now it has the same exact electron configuration as neon way over here on the noble gases. But not only does it have the same electron configuration as neon, more than that, now it has 11 protons, 11 positive charges, and only 10 negative charges. So I hope that you can see with me that these 11 positive charges, and remember where they're located, they're in the nucleus, all working together really tightly to pull these 10 negatives who are in now 2 different energy levels. So they are going to pull these 10 left electrons, and they're going to suck them in tight, so that this atomic radius, this ionic radius, is much, much smaller. Than its ion. Than its neutral atom.
Lady Hawthorne, come to the office, please.
And then the same is going to be true of chlorine and its ion. What happens between the element that is neutral and its ion, which it has to gain. This one has 17 protons, it has 17 positives, and it had to gain one, so it has 18 negatives. Is it going to get smaller or larger? I hope that you can see that since it has only 17 positive things trying to pull in 18 negatives, that it is not going to be able to contain them, and it is going to grow larger. So this is going to get larger. Now, not significantly larger as the sodium ion does, but anions do get larger than there. Okay, and it explains it to you here. Dr. Burdg does. So when an atom does gain or lose one or more electrons, it does get pulled in. The more electrons that it loses, the more tightly it gets pulled in. So, okay, I'm sure we probably can get a picture here. And then it shows you here why. Okay, and also a significant decrease occurs. Because not only do you have more protons than you have electrons, but also because now it lost that entire energy level. Okay, the reason that they become ions in the first place is so that they can become like a noble gas. And the closest noble gas has a full energy level. So remember why energy levels exist in the first place? It's where electrons are moving. And if there are no electrons in that energy level, there's no reason for that energy level to exist. So if you have sodium and it has one electron stuck out there in an energy level, it is creating that energy level. It is making that energy level as it's moving. If you take away that electron, there is no path for it. It's not making itself an energy level. So if you take away that electron, there's no energy level, and so it's way smaller. All right. Here's sodium, and there, see how that blue energy level is completely gone? So it is so much smaller than its neutral atom. Sodium ion is much smaller than its neutral atom. And then here's a picture that's also in your textbook showing how the metals on the left side here are significantly larger than their ions. But the nonmetals, look how much, there's not as much of a difference in the size between the nonmetals and their anions. Okay? All right. And then here you're going to have some like this. You're going to choose which ones have the same electron configuration. So you're going to actually have to write these electron configurations and then choose which ones have the same ones. And that's the only way that you can do it. All right. And then right here, just some general trends to finish up. You know that elements in the same group do act alike, they look alike, and they act alike chemically and physically because they have that same electron configuration. Okay, the S's, the P's, and the D, they might have a different energy level, but they have S1, S2, P2, whatever. Okay? And then it gives you that caution right there that, you know, sometimes the first element in the group, like, for example, hydrogen in the 1A is much different than the others. That boron is different from the others. Carbon is different from the others. Oxygen, much different from sulfur. So you got to be careful about that. And this is just kind of, you know, interesting fact, but it is true that you can have certain diagonal relationships between pairs of elements, like lithium does act like magnesium some, and so forth. Those are called diagonal relationships. It's just an interesting kind of fact. Okay. And then hydrogen, we've said this before, that hydrogen is kind of the lone ranger. He just belongs by himself. Hydrogen does. Okay, and then right here we've already talked about these. The group 1A elements, the most active elements, metals especially on the chart, they want to lose that electron so bad so they can become like a noble gas. They're so reactive. They just are not found by themselves. They're so active. They want to get rid of that electron. Okay, and so they're always going to form with water. They're going to react with water. This is why they're going to rust easily. In fact, potassium is so reactive you can't even store it in a can or a bottle. You have to store it under oil so that it can't react. It will pull the water out of the atmosphere and react with it and explode. So you have to be really careful. So the metal plus water is going to give you some metal oxide like sodium hydroxide, or lithium hydroxide, potassium hydroxide, plus hydrogen gas. Here are some examples, some pictures of these. And you see that in the beaker right there, it looks like it's sitting in water. It's not sitting in water. It is literally sitting under oil, and rubidium and cesium as well. Those are encased. The rubidium is even more reactive than the potassium, and it's not only encased in oil, it's encased in a glass tube that's enclosed so that it can't possibly. All right. So it just gives you these active metals, some reading for you to do in the text. Okay, and then you got the alkaline earth metals. These are your group 2A. These are what your alkaline batteries and so forth are made from. They're less active than your group 1As. But once it loses that first electron, oh my goodness, that second electron is going to go fast, fast. Okay, and here are some examples. You've seen magnesium before. Strontium is, some of you did strontium in your flame test, and calcium, you did calcium with your flame test. It's so pretty when it burns. You did that in your flame test, so you've seen this. And you know calcium reacts with water, calcium hydroxide. Tums, this is what Tums and some of those things are made from, so you've seen them. All right. And then you have your 3A. A boron is a metalloid, and all of the others are going to be metals. So boron's kind of an odd element. It doesn't form a whole lot of compounds. It almost acts more like a non-metal than a metal, but it's just kind of a different one. Okay, and then you know that aluminum, we use aluminum foil all the time. It's got many metallic properties, but aluminum forms aluminum oxide very readily when it'll rust easily. So you've seen that. So, and then here's gallium. This is the one I was talking to you about, that Mendeleev predicted a lot of the properties of it. So there those are, and then it's just talking about, here's carbon. You've seen carbon. One thing that carbon and these elements have for them is that they have a +4 or a -4. Most of the time, they'll lose their electrons, but they can do. They have an S2P2, and so they really can. So there you have those. Very interesting, and some of them very beautiful. Notice that carbon can exist. It has actually 3 states. They're called allotropes. We've talked about those before, but there's 2 of them. Graphite, like in your pencil lead, diamonds, and then you have some of the others in this family as well. All right. There's your nitrogen. I'll let you read those. That's in the text. And look at that red phosphorus. There's 2 different forms of phosphorus, red and white. Red phosphorus is what match heads are made from. So you've seen that. And then liquid nitrogen, look how different those are in that particular family. Very, very different. Liquid nitrogen is what they use to burn off your warts in the doctor's office. So there you go. All right. And then the next family, you know, so important, are your oxygen family. And look how different oxygen is from the others in its family. Sulfur, selenium, and then you have your halogens, the most active non-metals on the chart, and so important. You need to know those halogens. I hope you remember that their anions from that are called halides. Okay, very high ionization energies, very, very high electronegativities. They're going to form acids. Hydrogen halides are acids. So, and here's like chlorine and bromine. Bromine is unusual because it's a liquid. The others are gases, fluorine and chlorine. Iodine is also one that's different because it is a solid or a gas. There is no such thing as liquid iodine. It sublimes. It goes straight from a solid to a gas. So, all right. And then you have your noble gases. And then here are some of the examples of your noble gases. These tubes are used to produce what they use to make flame tests, are examples of flame tests for the electromagnetic spectrum. And so they're really beautiful. Some of the colors they produce are stunning, actually. We see them as neon signs, you know, but actually our neon signs don't just have neon gas, and they have other gases too. A lot of these noble gases. So, all right. And so that just gives you some ideas. And that's that chapter. So, pretty easy chapter. No math. That should make you happy. Get ready for a test. It's going to have mostly chapter 6 and 7, but we're going to pick up chapter 5 since we didn't have an individual test on that. And then we're going to finish out the chapter now. Chapters 8 and 9, I will tell you that chapters 8 and 9 have a lot of molecular geometry type things in them, but now Dr. Burke goes into a lot of detail, she does, and we're not going to go as in detail as Dr. Burge did, so because you have to really hang on to your hat, but we will get there.